While we wait for people to filter in, I'm going to go through the most exciting part of the presentation. There will be forward-looking statements in this presentation. Philip will act like he knows what he's talking about. He doesn't.
That's the most forward-looking.
In some cases, forward-looking statements can be identified as using may, will, should, expects. Forward-looking statements are based on what we know now. Don't make any assumptions. Don't bet any money based on what we're saying and then come to us and get mad if you lose any. We're just up here. We don't know what we're doing. Complete your surveys in the app, because everything has an app nowadays. So get in there, do your surveys, tell them you liked us, tell them that I was better dressed than Philip.
Lie to her.
Lie to me, like everybody else. Yes, go in your attendee portal and do these. I think someone actually reads them. So, leave some jokes, leave some memes, make it fun. And we will get started right now, right on time, because we have a lot for you today. So this is going to be maybe a bit of rapid fire. The way this is going to go is that Philip is going to talk through what he knows best, anti-cheat. I am going to do my best to play the role of you, the audience, and ask questions where I think that there might be things, unless you work in this industry, that you might not understand. So we're ready to go. You may now put on your 3D glasses.
I thought you were going to change that subtitle.
No, I left it. It was great. I thought they were going to make me take it out, actually, because it doesn't fit the branding guides. But here we are. So I've been talking. My name is Carly, for those of you who know me or don't know me. I worked on Call of Duty for about 5 years on live ops the whole time. I still have the scars to prove it. They're mostly mental. And I now make content on LinkedIn, and I work at Databricks as a field CTO in gaming. My best game, my favorite game, is Jurassic World Evolution 2. 3 just got announced, which I'm so jazzed about. And my biggest fear is not providing stakeholder value.
And I'm Philip Kaskinas. I'm the professor of anti-cheat at Vanguard Industries. That is the anti-cheat product, the PC anti-cheat product that Riot Games develops to protect games like Valorant and League of Legends. Well, most everything in this presentation will be about Valorant. But my best game is one called Super Hexagon, which you've probably never heard of, but I'm like number 4 on the leaderboard. Where are you at? 6. Damn. Let's, afterwards, maybe? And my biggest fear is male pattern baldness, to be honest. But I've dodged it so far. All right. So this is the menu. We're going to talk a lot about the types of cheats that affect first-person shooters, mostly. I am going to use a lot of Valorant examples. And you can see it here, so I won't go through all of it. But we're going to be talking a lot about pixel bots and about the DMA cheating vector, which, we can go to the next slide. So first up, encyclopedia. We're going to kind of describe those cheating vectors I just made mention of. And before I get into all that, I'm going to use Vanguard terms to describe some of the stuff that we do, but it's an active learning loop. Y'all are all data scientists, nerds really, so you probably know that we're basically utilizing the Vanguard product to query true false off of a client. That's how we kind of create the detections, but from that we kind of want to predict we're trying to predict the actions that our agents take. And it's actually a ton of effort to predict they're trying to basically predict bans, the likelihood that any one person cheats. And this is the core detection loop for the majority of anti-cheats. If you've ever worked on an anti-cheat, it's probably not too dissimilar from those. I used Vanguard symbols to highlight that this is a Vanguard presentation.
And if you are waiting for an architecture diagram for something like this, fear not, I have one for you later. So I see a lot of you getting uncomfortable waiting for that.
Quick note on the type of cheating. So, and Carly's probably going to have something to say about this because she worked on COD. A lot of games that are built in Unreal and haven't opened RPCs on the server, well, really, they have the ability to, it gives the game studio the ability to architect a server that is authoritative. That is, that it's simulating the majority of the game, and the client is only really responsible for making requests to it. This puts the developer in this position where they're kind of able to sanitize the majority of the exploits of old. The things that you probably think of when you think of cheats, like God modes or infinite gold, infinite cooldowns, things like that. When the server is responsible for simulating the majority of the game, you can outright reject the majority of this through either raw packet sanitization, parameter sanitization later in the function, or just Unreal actually does a lot of it for you.
What I will say here is that depending on the type of game you're working on, so specifically when I was working on Battle Royale games, there are times where you cannot be server authoritative. I'm talking about times like when you're in a vehicle driving around a map. The only way for that to work, to not feel laggy and terrible, is for that to be client authoritative, meaning that all of the calculations for how your vehicle runs, the smoothing, the way that it handles terrain, is all done locally on your PC or PlayStation or Xbox. So that means that things like that are a vector to get hacked, because anything coming from a client is inherently untrustworthy. But there are moments where you are physically, because of the laws of physics, incapable of making things server authoritative. So if you're designing a game, be mindful there.
That's true even in, I'll extend that. It's true even in the first-person shooter genre. If you've ever played Valorant, there are characters within that game that can blink. Their blinks are actually deterministic, so it can be a server authoritative, but that blink and that's low time to kill of the game necessitate that the client is given a little more information than it needs. And we'll get into a lot of that later in the presentation, but there are some concessions you have to make in certain game design loops where your server can't be authoritative. But because, we can go to the next slide. So because the type of cheating we were just describing before is something called internal cheating. So it's like basically you're trying to get code to run in the game client, or trying to read values, or you're trying to run something locally on the host for which the purpose is reading game memory or manipulating game memory to get the game client to send something to the server that it shouldn't do. That's like the typical exploit you're familiar with. But the majority of, like we're talking about with this server authority that we're going to baseline assume for the majority of the presentation, then all you can really do through this type of cheating is gain access to something called an ESP. You're basically able to exfiltrate the enemy positions, the enemies in Valorant or in COD or in Counter-Strike too. The enemies, you're able to get the positions for them and render them above the wall layer or on a separate radar.
Philip, what does ESP stand for?
Oh, extrasensory perception. Wall hacks is fundamentally what they're trying to, that's what's available in like a modern title. But it's not just reading. There are also writes that can allow you to do certain things, even in the most secure titles. You could hook get direction, for example, or actually a lot of the way they do it in Unreal is they hook a process event deep within the Unreal Engine and manipulate the parameters that way. It's everybody's favorite way to cheat in Unreal. But you're basically just updating your aim vector in game, and the reason you might want to do that is to aimbot. However, like we were talking about before, modern anti-cheat has for the most part rendered internal cheating, it's too detectable. The time to detection is too low. It's hard to productize for the cheat developer. It makes it difficult. It's prohibitively difficult to get into when you have, I'm going to use the word invasive, but it's more about the fact that there's such a clean perimeter around the game client that you can't really read or write memory from Windows without alerting the anti-cheat. So, as we'll get into this presentation, cheaters have pivoted into two other vectors that are definitely our favorite. One is pixel bots and one is DMA. And I'll do a little bit more on internal cheating if you take us to the next slide. This is kind of re-summarizes everything I just said. But as host security has improved to this stance where the perimeter around the game client is trusted, we basically know, we can rely on, especially on Windows 11, we can rely on a lot of hardware security features to know that the operating system is in a trusted state. And if it is, then we can trust that all the requests to read or write to Valorant's memory are things that should be doing, that. There are two ways that they typically get code these days into Valorant or any game client, and one of those is like just loading a signed library. And the reason it has to be signed is because, with code integrity validation, we can outright reject loading any library that is not properly signed. And you're probably thinking, well, cheaters probably don't have signed libraries because they're operating out of some basement somewhere, but you'd be surprised. They do get their hands on driver certificates for things like Gary's dishwashing service. Why it would need a device driver to instrument Windows is beyond me. But that probably seems pretty obvious, and it is. It's because obviously that cert has an entity, we can look it up, and we can just deny list it, right? It's one of the reasons that vector is kind of not viable for something you want to sell, because the minute 50 people have it, we're alerted to it, we deny list it.
So what you're telling me is that gamers hate kernel-level anti-cheat, but they would hate their lives more if it didn't exist.
Oh yeah, easily. Well, especially for competitive games. And I think that's I don't want to spend a ton. We would be here forever if I justified all the reasons we need a kernel driver. But primarily, it's so we can do things like this second one, which is
Sorry.
the second one, which is leveraging cheaters leveraging drivers of their own, or leveraging a vulnerable driver to get their code into kernel memory, or mapping it in manually. There's a ton of ways they basically get code into Windows kernel. But when they do that, if we don't have kernel anti-cheat, then all the calls we'd hook from user mode to try to alert ourselves to a read or a write occurring would be subterfuge. They would be able to do it as if they were Windows itself. Like one of the things that we get with this on-boot kernel driver is we have the ability to measure every driver that loads from Windows Start, measure it into the TPM, and then through that we can kind of use it as this secure chain of trust to know if Windows itself was ever broken. That is that one, it's the who loads first problem. If their driver loads before us, it can load in and then scrub itself from any telemetry that we might be able to obtain. So we load first and deliberately measure every single driver that's loaded into the trusted platform module. The reason we won't get into a lot of this is because it gets a little technically complex, but that's just the high-level overview of what internal cheating is. And now we'll get into the meat of the presentation. It only took 10 minutes. Okay.
We're right on time.
Let's look at some graphs. I just said that. You'll notice that the y-axis in this one has been elegantly scrubbed. But what you're looking at is the number of matches. We call them infected matches, basically a match that has at least one cheater in it in Valorant. And you can see all the types of cheating on the right there in the legends. And the three that we talked about before are the internal cheats, which are rendered in the yellow. You can see there are a lot of them. And then also the pixel bots rendered in the green, which we're going to get into, and the DMA cheats, which are red, a very small subset of players, and you'll learn more about that in a minute. You're also probably thinking that, Philip, why would you use a stacked area graph? My eyes can't consume this or compare it in any way. If only you had normalized them to each other or done something like a percent. Yeah. So anyway, this is a stacked 100% graph of the same thing. And one of the things I want to highlight is that as I was talking about before, as host security improves, as we're able to outright detect and reject these internal cheats, we're seeing a greater percentage of both cheat developers and the productized cheats themselves, and the matches that are affected by pixel bots and DMA. And DMA goes through waves, and I'll get into that in a little bit. But we are seeing somewhat, it's been seasonal, and the seasonality is actually from when our anti-cheat is its strongest, like when we're on top of our game and know all the cheats, and then we kind of wane, and you can see that the internal cheats come back and then we get strong again. But we are seeing, especially in the last 3 years, an increase in the number of people that are looking at these external vectors, Pixelbot and DMA.
Cheaters seem pretty active in January. What are they up to?
They don't have school.
Oh.
Yeah. Also, we go on break and the timing could not be worse. So most game studios have a winter break and cheaters.
It was always the worst coming back from that and realizing.
You know from experience, I'm covered in scars. So Pixelbots, at its base layer, I know I said I wouldn't talk about internal cheats, but there are both internal and external Pixelbots. I'll explain what I mean. But at its base layer, just imagine that your mouse is basically aiming for you. Remember, the client's basically secure, so they can't hook set direction within the game client like we had talked about before. They have to instrument their mouse directly. And there are two ways they do that.
So why get good when your mouse can get good for you?
Yeah,
that's
my favorite quote. Imagine your mouse had a magstripe reader and you could just pay it to play the game for you.
Wow, that sounds amazing.
Why would you do that? You wouldn't. But
I have friends.
Man, cold. Some cheaters have friends. They also cheat. All right, so what you're looking at here is internal versus external Pixelbots. And I'll briefly kind of summarize. So an internal Pixelbot is something that is, remember, they're trying to manipulate the mouse. To do so, they have to read the screen for the opponent outline. Basically, they're trying to update. I'll give a pretty good example of it in a minute. But they're trying to identify the opponent head or the opponent outline and then adjust the mouse to aim at it and then fire. It's an aimbot, but it's an aimbot implemented totally outside of game memory. They're either using a screen classifier or they're just doing something like a simple color sampling algorithm to try to identify an opponent outline and then update the aim. If they're doing it internally, what this means is that the screen reader, the thing that's looking at usually the center 300 by 300 pixels around your crosshair, that screen reader is local. It's running on the host, which is good news because it means that we can probably find it. If it's external, and this is where it gets kind of crazy, they are doing it totally off the computer. And I'll explain more about that soon. So this is what an internal PixelBot looks like. You basically have your mouse going through an Arduino or a KM box. It's basically it's a microprocessor for which the purpose is, it is basically able to put instructions between what you did with your mouse as a human and what the game client eventually receives. And the reason I've put a little lock there is because kernel anti-cheats, the one that we develop, has proprietary techniques to ensure that only one device is able to submit direct input to the game client. So they can't have they couldn't use virtual input with a script running locally. It has to come from the mouse, right? So this is how they beat that. Now, in the internal PixelBot architecture, that Arduino is still connected only to one PC, and it's being instrumented usually by a Python script that is running like an OpenCV library. Anyway, next. Here's an example of a typical internal PixelBot. You can read that subtitle there because that's a little bit of a warning. Don't make me do it. I don't want to do this to you. It hurts me as much as it hurts you. Every time I swing the hammer, a piece of it swings back, and it hurts. Anyway, here's the second thing I was getting into, the 2PC PixelBot. Now, if you're running that Python script locally, like I was talking about before, we're going to notice that Python is reading the screen. That OpenCV library, there's a ton of them that can be used to accomplish it, but eventually we're going to notice that the thing that's reading the screen doesn't have any right to be. And
so I shouldn't have triggerbot.py open while I'm playing? No?
Well, no.
Okay. I have to buy a whole second
It is funny you should bring
for
up. So triggerbots are actually the most common type of internal cheat, and I don't want to spend a whole lot of time on it. But a triggerbot, the difference between a PixelBot and a triggerbot is a triggerbot is only firing, which is not as relevant in high time to kill games, but in games like Counter-Strike or Valorant, where you have an op or an optical. You literally have a scope on your sniper rifle and can look at head height across a corner, and literally the minute that a head enters it, you'll fire. But anyway, advanced PixelBot is something that, and this is the 2PC cheating we're talking about, is basically, imagine a cheat that runs completely off of the host like we were talking about before. You still have that Arduino or that KM box, but instead of being instrumented from the main PC, it's actually instrumented from a totally separate PC. And you only need to get screen data undetected to that PC. And there are 3 ways that people typically do that. One is leverage OBS. This is actually the fastest one, curiously enough. The fastest way is actually just to stream the 300 by 300 pixels at the center of your screen, and then just have your second, on the wire, your second PC just reads the MBD packets. But that's probably the fastest, but it's actually not the most popular. The most popular is a capture card. So you just have a capture card, and we don't know if you're using that because you're the most popular streamer in North America, or because you just are recording all your gameplay. There are legitimate use cases for a capture card, right? So we can't, and you'll notice that cheaters try to use things for which there is a legitimate use case because we can't deny it. So we have to allow capture cards, but you could be using them to just send your screen data to a second PC. And the third way is an HDMI splitter. This one's the least common, and it's because they're expensive. They add a lot of latency, and the only ones that don't are basically another graphics unit. And they cost like $400 to $500, and it's just too large a price point for the people that want a color bot. Oh, you also see me use PixelBot and ColorBot interchangeably. They're the same thing. And the final thing I'll say is once it's on that second PC, in Valorant, I would like to pretend that the cheaters are smart enough to be doing screen classification or trying to do object detection to find enemies to click on. They're not. They basically just set their player outline, because it's configurable for colorblind accessibility. They set the outline of the enemies to something outright like purple, pink, something bright that doesn't appear in the game otherwise, and then they color sample the boxes in the center to find which one this one has the most pink, I'll sample that one. And there's no classification whatsoever. It is just a straight color sampling algorithm that's trying to identify where an enemy outline is.
How often do you fight with your devs about removing those outlines?
Constant. Well, I've given up. So originally a lot. But they think and I think they're correct, is that a lot of the accessibility of a tactical shooter is dependent upon the visual acuity of being able to identify an enemy. I know that I hated Counter-Strike because of all the camo. So I think that they gotta be right. I give it to them, it's a popular game, people love it, or we wouldn't see so many cheaters. So yeah, like we were saying about before, once that second PC is in play, there's a lot of spare there's a lot of spare graphical you have another GPU to utilize, right? So they could use screen classifiers, and they do in games like Call of Duty, where the outlines aren't as bright, or even in Fortnite, where there's just so many colors, it's not as applicable. So they actually are using simplified object detection to try to find enemies to click on. But this is not the case in Valorant. It is usually just color sampling. And then you're probably asking, actually you're probably not asking, maybe Sarah's asking, Phil, why can't we just, you notice that an Arduino is connected to the PC? Well, they do a thing called USB pass-through, which is basically any query we could send the USB controller for that device. They just take it and send it to the mouse that's connected to it, and then reply with whatever the manufacturer intended for those things. They don't do it perfectly yet, but they're so damn close that we're worried about banning everybody off of the remaining detection surface, because we would it would set us up for the inability to create ground truth to the models we're trying to develop to address this stuff. Last thing I'll say is that, like, you saw that green graph before, which was a comparison of external and internal pixelbots. External pixelbots are about 15% globally, and it's growing by about 0.5% a month. That is, they're completely external pixelbots. They're no longer reading screen on the host. They're doing it by one of the 3 methods we talked about before. And that's got to be your... Yeah, that's your... I can always tell when it's one of your subtitles. But yeah. So how can we beat this stuff? I kind of already brought up some queries we can send to the USB host controller that would try to make it reveal itself. But after that, and after you've kind of secured direct input to only have one device, it sucks to say this as an anti-cheater, but that's all the detectable surface you have from the host. Everything else is scrutinizing raw input or scrutinizing server-sided aim vectors. And there are some prevention methods that we won't spend a lot of time on because I want to get to the rest of the presentation and leave a few seconds for questions. But there are things you can do, like Carly brought up before, where you can manipulate, to make it more difficult to color bot, you can manipulate the outlines in game. Let's get into first we'll get into the...
This one was you.
Yeah, that one was me. So a lot of what I'm saying is that they're instrumenting their mouse externally, and we're trying to basically determine that it's inhuman input, right? This starts to become a war of algorithms, a war of machines, really. Begun the machine war has, and we're basically trying to identify that the raw input coming from the mouse, or even the server-sided input, the server-sided aim vectors, are inhuman. We'll start with raw input classification because that's probably the one that has the highest granularity. I don't know what the tick rate is of every game server out there, but Valorant's is pretty fast. And even with that 120 tick rate, we can't, it still takes us a lot of samples to actually know that a player is not human, that aim is not human. Whereas raw input, we can sample, utilizing Vanguard, we can sample it at the exact same polling rate that the mouse is. What you see on the left here is actually something called a recoil bot. It's basically like, it's every time you click, it's moving your mouse subtly downward, trying to correct for the recoil from firing the rifle in the game. But one of the things that doing this kind of raw input classification necessitates is that you have like superb security posture, because one thing I mentioned before is that they can actually just hook direct input in the game, and if they do such, then your hook on raw input would receive nothing for the updates that the aimbot is making because it's instrumenting them directly in the game client. So just and also kind of like if you just, let's say you had a user mode hook for recording input, it could be instrumented by, a cheater will eventually find that and perform a sort of replay attack where they send a different set of data that's known human while they continue to cheat at game. So you actually need a pretty secure setup to even get into this game, but once you are, you can start to sample, it's actually just time series data for mouse input, the delta in XY at the same frequency of the mouse. And there's probably 2 modeling approaches we've tried. There's obviously the 2D convoluted neural network that, nerds in the audience probably already saw this problem. We're like, I would love to throw that at it. It works. It actually works very well. The issue is actually that you need ground truth. You need cheat data that you have to cook yourself. So you can either outsource a bunch of people and have them be cheating all the time, or you could just have an anti-cheat that labels all the cheaters for you, and it kind of closes that active learning loop we were talking about before, and makes it really easy to identify anomalous mouse stuff. There's also vendors in this space, and I'll give a shout out to AnyBrain. That's one of the ones that we've done a lot of research into. And they're probably they're the most game agnostic one. Like they've trained it on everything they can. So their synthetic moves model is best positioned to detect like a wide variety of pixel bots. And I make one note here that if you are trying to do this, if you are a game studio, don't interpolate or downsample the mouse update. You're gonna be encouraged to do this to reduce the size of the array you basically have to send back to your server. But don't, because it'll inevitably smooth the aimbot. There's nothing you can do to kind of avoid this problem, but if you downsample the granularity, you'll lose visibility into the subtle adjustments that the aimbot is making, because it's basically an aimbot arguing with a human, so you need a high sample rate. Next.
One thing I will also say, as Philip talks about, the issues that you have with sampling in the mouse and then your tick rate on your server, right, that you're losing information from the server, basically not refreshing that quickly, is that the same thing happens with your kill cams. So if you're looking at a kill cam from a game to tell you what actually happened and whether or not you were hacked against, you're starting with a half deck of cards, right? That's not the reality of what happened in the game world. And so you are also falling victim to the same thing where the data you're looking at is not complete.
Really great point. And I'll add that as games release replay systems that are reliant only on what the server sees, if there's no lag correction, if there's no package drop correction, sometimes you'll see something we like to call a hackization, but it's basically players that see a snapped kill cam, and even if that the client dropped a bunch of packets in between the update, all the server saw was not pointing at head to pointing at head, and because so much of anti-cheat is the perception of cheaters within the game, replay systems can actually become a pretty big enemy if you can't educate the player on how they function.
So now you all know, and now you all have to go out and tell everyone else. We're relying on you to educate everyone else, okay? We're gonna check in a couple months and see if you've been evangelizing that kill cams will wreck your shit. Okay.
So this is server-sided classification, which is not as good due to the granularity thing that we kind of already highlighted, but it is really good at drawing a line around what's humanly possible. And I mean human performance within the game. I have a member of my data team here with me today that probably recognizes these PR curves, but these are us attempting to basically, from just the aggregated in-game direction behavior, trying to determine if the person is a human. And it's imperfect. Obviously, we're not able to take immediate action. It takes, I think we need like 6 games of you rage hacking to really get you out of game fast enough. But it's that layer doesn't rely on us exfiltrating all that mouse information and getting it through the inference. It is really just looking at the server-sided aim samples and aggregating them in, well, some of it's aggregate, and then there's a couple of things that are simple, like you can just look at the maximum mouse velocity, because anybody that's like clearly just running a rage hack pixel bot is gonna snap all over the place instantaneously. And you can kind of draw a very obvious line around what should be humanly possible within the game, and anybody that goes outside of that, you can get them out of the game faster. The difficulty in this approach at that granularity with aggregated features is that a lot of pro players, when they hop on their alternate accounts at lower MMRs, they massively overperform. I mean, they're basically a very high-rated player playing against people who are totally new to the game, and they just stomp them, and they'll inevitably look like cheaters to models like this. And that's something we're kind of, and you can actually see version 1, which was like 3 months ago, and then version 2, which was like last week. So it is improving very quickly as we figure out like which features we need to add to improve our rage hack detection.
So if you are building a game, one thing I will say that Philip brings up is that the more people you have in your lobby, the higher likelihood you have a very great skill disparity in your lobby. So if you have like pro players smurfing and they're in these lobbies where maybe they don't look like they're that good, but they're actually really good, the high skill disparities can really mess with your behavioral anti-cheat, because you're doing these aggregations on filters, you're looking to see, is this person performing above what we would expect for someone at their level or for someone in this lobby, right? You have an expected outcome for every lobby matchup. That's what matchmaking does, right? You can kind of predict who's gonna place what in any game match if you know their skill ahead of time.
That's why we put ranked rating as a feature in the model.
100%.
Okay.
Yeah.
Oh, I was going to make a joke earlier that I really regret not making. But on the raw input classification, we actually had a lunatic on our data team that just threw like ResNet, like literally on the graph you saw of the user's input, and it performed as well as the time series model. I mean,
great.
it is two-dimensional data, right? So it's a longer way to get to the same thing, but it was just, what a lunatic. So here's a kind of looking at those behavioral things we've created that are meant to address pixel bots, and as you can see, my analytics team is just getting lazy. No, I'm kidding. So the bottom, the darker blue is the manual bans, basically somebody that reviewed input, reviewed actions taken in a game and determined them to be cheating, and the light blue is that slowly being totally replaced by the models. They're coming for our jobs, and it's all over. No, obviously we still have to, a lot of the review takes longer now because these are things that have bypassed the model. They're performing within human means, and it's an arms race with anti-cheat. So we're not getting as many obvious cheaters to review, but we're finding new things. And, oh, this is your slide.
Oh, yeah. So this is something that I actually built during my time at Activision with someone I was working with at Stanford. So what we were trying to do was, basically we were messing with all different kinds of cheats that we've talked about today, internal and external. But I think this goes well with what we've been discussing here, which is, can you confuse a computer vision algorithm by putting things into the game that maybe shouldn't be there? So with this example, we called this hallucinations. So we were actually fighting internal and external cheats, like I said. From an internal perspective, the way that we injected these into the game client was actually pretty brilliant, if I say so myself. We were, per client that we suspected to be cheating, inserting a new player into the snapshot in memory getting sent from the server. Because if you do this, if you basically put a bot into the game and have cheaters say like, oh, if they shoot at a bot that's hidden behind a wall, they have a wall hack. That's great, but they'll just actually look at the server snapshots, delta when you actually put this thing in, and know it's not a real player. So we had to have the match from their perspective start with this player that from looking at the snapshot you would assume was real. So what we did was we just actually did a memory copy of another real player in the game. So when you did this in production, it was funny. You could just pick a random person, like playing Warzone, do a mem copy of them, inject them into the snapshot of the cheater, and they would see this person doing whatever they were doing, but from a different part of the map. So they'd be like trying to run through a door. So it would just look like someone like not knowing where they were, because they weren't actually in that part of the map. It was just a copy. So you can do this, though, to also confuse like a computer vision system. So maybe with the outlines, you could start to make the outlines a bit fuzzy. Do something if you're running a true computer vision, they're pretty brittle to things that change. So change the color up a little bit, something that the human eye—
Turn the whole screen pink for one frame and see what happens.
If it shoots at everything, right? Like, you could get really complex with this. So you can spawn fake enemies within geographies. You can spawn it outside of the map and see if they're, actually with this ESP, extrasensory perception, hovering over things. There's all sorts of things you can do when you have control of the server as well, right? So this idea that the server is an authoritative owner of the game state is pretty great when you own the game state. So you can put things in the game state to confuse the cheat. And that's something that we like to do. And I did this subtitle too. LLMs aren't the only system that hallucinates.
Lamau. I'm sure this audience really appreciates that.
Oh, God.
They really appreciate your humor.
It's my time to shine. Here's the architecture diagram, you guys.
Here's the
Get ready for this. Everybody take a picture of this. Post it on social media. It's beautiful. I made this
If you take away
myself.
one thing from this, it's that you could host the majority of your anti-cheat processing on Databricks.
You could,
That's what
if you wanted
take away.
to, and you should, actually, if I do say so myself. So if we
Where do you
look
work
here,
again?
I don't know anymore. If you look here, you'll actually see we have our sources for anti-cheat. You have your server-side data coming in straight from your game server. You have your client-side data, which is either your mouse or coming from a phone if you have a mobile game, or coming from PCs. And then we have some unstructured and semi-structured data as well. So like files and logs coming from, say, your kernel driver, or crash logs from a server, anything that's not fully structured. You can use an ingest tool to handle your semi-structured or unstructured data. And then you can actually just straight up stream live stream your client-side and server-side data. So if you can unify that, do it live streaming, then you can do things like live machine learning, right, on your live data stream, which is pretty cool. So using MLflow or your Databricks notebooks, you can then serve your models in real time and get them out to make determinations. You can also, let's see, what else do we use here? You can use Delta Live tables to get all of your ETL running and get everything in the way that it should be. And then Databricks SQL, you can have your analysts actually use that as well to look back or look at matches once they finish. You know, usually running on about a 15-minute round trip journey from a match to finish for the data to be available if you're not doing any sort of real-time streaming. And then you can hook that up to your BI tools. You can make graphs, like Philip makes graphs. And then you can get up here one day and show your graphs off to
bar
people
charts, Kaskinas for nothing.
trying not to fall asleep because they've been looking at graphs since, what, 11 a.m. this morning? We're sorry, we didn't want the last session
That
today.
was the one shilling slide. They don't call me Shillip Kaskinas for nothing.
Shillip, oh, I like that. Well,
right.
I'm Shillip now.
This is the fact that pixel bots also exist on consoles. I won't spend a lot of time on this slide, but it's a vector that's anything with a screen you can really do it on. And that is another one of your subtitles.
I know. I feel like I'm not getting enough laughter from these. Like, guys, with a screen and a dream, you can cheat on anything.
It's so good. But yeah, obviously, I briefly visualized the two-dimensional input there, and you can see that the console is obviously, when the input is in human, it kind of lights up the same way. You can approach it the same problem the same way. DMA, this is the next vector that we're seeing a lot of. This is basically a very niche way of hardware cheating. It's growing in popularity. It's been around for like 10 years, but it's using physical hardware to read the physical memory of the computer invisibly to the operating system. And this is kind of what it looks like. You have your main PC that's running, the anti-cheat, and it's running Valorant, and then you leverage a DMA card, or a PCIe DMA card, to exfiltrate pages of client memory to a second PC. It interprets those regions of memory. It tries to find the enemy positions, and voila, you have a radar. And that's what baby's DMA looks like. Wow, you're rushing me.
We have 3 minutes left. We want people to ask questions.
Okay, so, and then obviously there's ways to prevent this that often kind of, we're talking about how much, the whole reason it's viable is because the client has information that it needs a little more information than a player should have, so even though it's not rendered to them, it's still there. So trying to get a perfect fog of war system could completely eliminate the vector, but like we were talking about before, we have to bake in some forgiveness into the game design, or players would just pop in when they teleport if you don't actually know that they're coming. So to make sure it's really smooth and to make sure it feels really snappy to the end user, the client is given a little more information than it needs. You can also encrypt these objects, but that is honestly out of scope for this talk and is something that would probably confuse us. Was that mine? All right, next. So this is where they kind of go, this is kind of where they go when they're total lunatics. Could you imagine having more PCs than friends? Anyway, they basically, the same as before, the PC's totally on, the entire cheat is implemented externally, but you also leverage a KM box, just like in our PixelBot example, and then because you have access to positions that you've exfiltrated from memory directly, you don't need to read the screen to find them. You have in-world real positions. You need only translate those into 2D transformations for your mouse, and then instrument it the same way you would a PixelBot. And this, I hate to say, is something we see more and more every day. We really think the parents are responsible. And DMA is growing in popularity. It's something that we have developed. We've spent a fortune on the capability to detect, and there are ways to do it. But mostly what we do is actually a blocking pattern. PCIe cards, for the most part, aren't necessary when you're playing a game. I know that sounds strange. But like if you think about a printer that's connected through a PCIe card, or anything that isn't really a network adapter is probably not necessary. So the majority of DMA firmwares can just be outright disabled, and we do that. And that
so I'm not allowed to screenshot myself playing Valorant and then print it off immediately?
No, I don't know why you would want to do that.
Because I put screenshots on my fridge.
Yeah. Cortana, log that one. That was a great kill. It's just like your dot matrix printer slowly fires up. But yeah, you can block a large percentage of these devices because a lot of them are very niche, and they really don't have any need to be operational while the game client's running. SIGing the device itself, it obviously has a a config space that you can access with kernel anti-cheat, and you can try to identify something that is specific to a cheat. But honestly, these days, the config space is honestly one-to-one with a real DMA device, so it's very difficult to just outright detect a specific cheat that way. So most of the defense comes from like tightening the requirements on the host machine. So like leveraging things like TPM 2.0, hypervisor code integrity.
Anyone here from Microsoft?
Yeah, I mean, we really...
You want to talk after this?
Please. But the problem with requiring these, and IOMMU is another one, we can start to leverage the memory management unit to secure pages of memory from DMA reads. But to do all this, we also need pre-boot DMA detection and kernel DMA protection to be enabled by default. And as a studio, we kind of inherit all that friction ourselves when we go to enforce it. And that's kind of like that risk loop I was showing out before. We try to selectively enforce these things in our most competitive and riskiest segments because it is a lot to ask somebody like, could you enable secure boot? Especially like a 15-year-old gamer. It's like, could you go into your BIOS settings? Don't mess up, because that would be really bad, and do all these things. And it's a lot of friction, so when it's not enabled by default, us making that request is a lot. And that's
All right,
it.
we have no time to
for
scare
questions.
you.
Oh, one more thing. This is worth saying. Give me one more.
Okay.
I get one more. So this is the time to detection for any of those cheats we talked about during this whole presentation. And as you can see, the ones that are external, the DMA and the PixelBot, they take us longer to detect because we're leveraging either nascent, incredibly obscure hardware techniques to detect something that's a DMA card, or we're having to leverage a lot of AIM sample data to know that you're using an external PixelBot. This makes them it lets them infect more matches because they're playing for longer, but it also means that in the infinite cat and mouse game that is anti-cheat, these types of cheats are slowly being prioritized. So, you know, you're in this talk because you're a data nerd. Now is your time to shine. Like, we did our job. Host anti-cheat, we're done. I did it. It's secure. Now y'all got to detect mice. Or actually, you got to detect this. This is the last thing I'll leave you with.